And nobody has any issues with 9 to the 3 halves. We talked about that the other day. For the benefit of the people who weren't here the other day, 9 to the 3 halves. Remember, when you're not here, you're supposed to watch the video. 9 to the 3 halves means what? Square root of 9 cubed. So the square root of 9 is 3, and 3 cubed is 27. Now, when we throw a negative in on top of that, we know that what that means is 1 over. So we start with 1 over. And as soon as you do the 1 over, nothing changes but the negative goes away. So now I still have 8 to the 2/3. What is 8 to the 2/3? The cube root of 8 squared, which is 4. So the answer would be 1/4. Now this isn't a fractional exponent, but it's a negative exponent on a fraction. And what does a negative exponent on a fraction do? Flips it. So this becomes 2/3 to the 3rd. When we take the fraction to the 3rd power, we take the top and the bottom to the 3rd power. 8/27. Anybody have a question about those? Because from now on, I'm just going to assume you can do those. Okay? Now, these are operations with exponents. These are examples of exponential functions. Now, was the exponential one of our BFFs? Yes. What was that equation? Do you remember? Y equals e to the x. Very good. So while this one is 1.14 to the x, the basic one you memorized was e to the x. E is just a number, 2.718 approximately. You can have any base you want. Do you remember the shape of this guy? Yep, that's it. Goes through the point 0, 1 unless we make some modifications, and it looks like this. It has an asymptote here, right? We get closer as we come out here, and it shoots off into space. When people talk about exponential growth, or something growing exponentially, what they're talking about is it gets really, really big, really, really fast. All right? Now, I'm going to look at this one first. This is an example of an exponential. In your basic one that you memorized, there wasn't a written or expressed coefficient out here. There actually was a 1. It's 1 times e to the x. In general, your exponentials are a times b to the x. You can have any number you want out here in front, positive or negative, not 0, obviously, but anything other than 0. Your base, on the other hand, must be a positive number. Your base has to be positive in order to have an exponential function. If your base is negative, you get a picture that looks different than that one. Okay, now I want you to think about this problem right here. We're going to look at this one. A is 200 and B is 1.14. What happens if I let x be 0? In this equation right here, what would happen if I let x be 0?
It would just be 200.
I would just get 200, because we know that when you raise something to the 0th power, you get 1. So if x were 0, this number would be, or the answer would be 200, right? That is why this number, A, is called the initial value. It is the original value before you start multiplying by 1.14s. If you don't multiply by any 1.14s, you get 200. That's called the initial value. So if this equation represented a population of a city or something, we would say, well, we're starting with 200 people. Now, what happens when I multiply it by 1.14? First of all, it gets bigger. By how much? well, exactly 28 people this time, but if you multiplied by another 1.14, it would be more than 28 people the next time. What percentage am I increasing by? I'm multiplying by 1.14. I'm multiplying by 114%, which means I'm increasing by 14%. So this equation right here, whatever it's describing, says I'm starting with 200 and I'm increasing 14% each, what happened to my exponent? Each x. So if x is in years, then every year I am increasing 14%. If x is in minutes, then every minute I'm increasing 14%. Now, with that in mind, look at this exponential. What is that equation telling me? This is an A and a B. Tell me about that situation. DeAndre?
It's going to be decreasing instead of increasing.
Absolutely, and it's decreasing because the number that I am multiplying by is less than 1. Now look up here. This number was more than 1, right? How much more than 1? 14% more than 1. So this was an increase of 14%. This number is less than 1. How much less than 1? 25%. So this represents a 25% decrease. It does not represent a 75% decrease. Don't you ever tell me that. If you are multiplying by 0.75, that means you are keeping 75%, losing 25%. Right? So whatever's going on here, we're starting with 1,000 and losing 25% every year, every minute, every week, whatever that is. X minutes. I'd be losing 25% every minute. All right, let's come up here. What's this one? What's going on here?
Decrease.
It's a decrease. What is the percentage decrease? How much is it going down by? 0.125, which would be a 12.5% decrease. Starting with how many? 3? So if this were a money problem, you've made a bad investment. You started with $3, but every month it's decreasing 12.5%. If it's a population problem, something's happening and your population is falling off, decreasing. All right, what about this one? What's going on here? This is an increase. What percentage am I increasing? 3.5%. This is a 3.5% increase with an initial value of 100. So if someone said to you, what would the equation look like if you had an initial population of 5,000, so we had an initial population of 5,000, and it's decreasing 10% per year. What would that equation look like? Y equals what? 5,000, initial value, 5,000, times what? 0.9 to the x. Does that make sense to everybody? What if it were increasing 10%? I would do exactly the same thing, but this would not be a 0.9, it would be a 1.1 if I were increasing 10%. We in agreement? All right, let's see if we can write one now, giving a little bit different information. Exponentials are easy. Oh, by the way, when they're increasing, they're often called growth problems. That makes sense to you, right? When they're decreasing, they are called decay problems. That makes sense, growth and decay. Things getting bigger or smaller. All right, let's try this. let's say we have an exponential function. So in other words, we have something of the form y equals a times b to the x. That's an exponential function. And we know it contains these 2 points. That's all we know about it. So we have this equation and it contains those 2 points, and you're going to write the equation. Does anybody have a thought about this? I think you have a thought. This is our form that we're shooting for, right? This point right here is kind of special. Exactly. If you think about this as an x and a y, if you put in 2 for the y and 0 for the x, isn't that going to give you your initial value? If the exponent is 0, that's going to be a 1. Doesn't this say a equals 2? Right from the beginning?
Yeah.
So I know right from the beginning my equation is y equals 2 times b to the x. Now what if I took this point now and plugged it in? So I'd have 9/2 equals 2 times b to the negative 2. A point, remember, is just an x and a y. Okay, how would I go about solving that? Divide by 2. Since fractions are involved, I think I'll multiply by a half. It's easier for me. So I have b to the negative 2nd equal to what? These cancel, I multiply by half. 9/4. Uh-oh, I have b to the negative 2nd. Watch it. That's 1 over b squared. So 1 over b squared equals 9/4. What do I do with that? Cross multiply. So 4 equals 9b squared. B squared equals 4/9. And what's my b value? 2/3. So all that work and I got my answer. Y equals 2 times 2/3 to the x. And these parentheses aren't necessary, but I'd like you to kind of maybe get in the habit of putting them in simply so that you're not tempted to multiply these two numbers together. You're never going to be able to multiply your A and B. Kids always try. Don't do it. A and B are separate numbers. You okay with that? Now, I want you to look in your book now, quickly, just because they set it up a little bit differently than I have, and I want to make sure you're prepared for that. If you look on page 286, if you look on page 286, down at the bottom of the page, it says, in exercises 11 and 12, determine a formula for the exponential function. In other words, y equals ab to the x. I'm on page 286 looking at problems 11 and 12. 286, 11 and 12. It says determine a formula for the exponential function. That's exactly what we just did. But they gave you the information in a table of values. I just gave you 2 points and said use these 2 points and go. They gave you a whole table of values. So if we're doing, for example, problem number 12, it says use the x values and the g values. Problem 12 is the g problem. So your table of values would be -2, 108, -1, 36, 0, 12, 1, 2, 4, 4/3. There's your table of values for problem number 12. Do you see that? Now, I did this problem. We did this problem a minute ago. And how many points did it take?
2.
2. They gave me 5. You got way more than you need here. But let's choose wisely, because ultimately you're picking the points you want to use. And any 2 will work. But I'll tell you what, if you want to get done quickly and easily, what point are you going to start with in that list right there? You're going to start with this one, because you know that if you let x be 0, this is going to be your initial value, isn't it? So we know right from the get-go, if we use that point to get us started, that we have 12 times b to the x. Because that 12 is our initial value. Now, you got to pick another point. Makes no difference which one you pick, but this one would be the easiest. Why would that one be the easiest? Because, well, it's the smallest, but look, x is the exponent, right? And isn't it easiest if the exponent is just 1? Now, you're going to get exactly the same answer no matter which point you pick, but I'm going to pick this one because it's the easiest. So I have 4, because that's my y value, equals 12 times b to the first. So what's b? 1/3. So my equation is y equals 12 times 1/3 to the x. Do not multiply the 12 and the 1/3 ever.
When you pick your point that starts with 0 as the x, and you get like your y,
Yep.
is the y automatically going to be the a?
Every time.
Every time.
That's your initial value. Yep. If your exponent is 0, this part of the problem is going to disappear, DeAndre, so it's automatically going to be
A every time.
A every time. All right, we good with that? Okay. Now, also in this first section, and I'm kind of combining sections 1 and 2, there's a conversation about logistic functions. Now, do you remember your logistic function?
No.
Okay, yeah, that's a tougher one. That's probably, of all of them, it's the one we paid the least attention to. But it has a very definite purpose, especially in population studies. Thank you. So we're going to take a minute and look at it now. We're going to write our own equations. But when you write an exponential, this is the format we're going to use. When we write a logistic function, there's a lot of variability. We're going to keep it simple. Our logistic functions are going to look like this. This is how we're going to write our logistic functions. We're going to have an a number up here. We're going to talk about that number. That's a very special number. And then a b and a c. This is going to be a 1 for us. Now, in the real world, this number is not always a 1. You can always make it a 1 by doing some division, but we're going to go ahead and just start with it as a 1 every time. All right, so here we go. This is going to be the given. We're going to write our own logistic function, and we're going to be given that the initial value is 5/4. The limit to growth is 5, and it contains the point -2, 2079. So this is the given information. Having already had a conversation about the exponentials, can somebody help me with this? when I say the initial value is 5/4, think about what DeAndre just asked. What can you tell me about a point that this represents right here? What point does that represent? What?
0.
If x is 0, then y is going to be 5/4. So this represents the point 0, 5/4. DeAndre said, if x is 0, will this number always be the initial value? And the answer I said was yes. Same exact concept over here. The initial value is really the y-intercept. What is the value of y when x is 0? So that is a fancy way of giving you that ordered pair. Okay? Now I want to talk about this because this is really important. Anybody remember what the logistic function looks like when I graph it? Oh, yeah, I remember what it looks like.
Is it like that?
No. Well, I don't know. Do it again.
Like it goes between like.
It
1
goes
and negative
between
1.
two asymptotes. Now, actually, it goes between 0 and 1 normally, but it goes between two asymptotes. You're exactly right. Remember, it's kind of that sideways squiggle. It looks like this. This is your exponential. And in the BFF, in the actual basic function that you memorize, this was 1 and this was 0. Okay? Now, this is going to stay 0. But this actually can be adjusted, and you should know that because we've moved things around, right? We've stretched things and shrunk them. So by putting a multiplier in the problem, we can move that. But this asymptote, regardless of what it is called the limit to growth. Now think about it. Does that phrase make sense?
Yeah.
Yeah, because the curve is not going to go any higher. That's the limiting factor. The limit to growth, if you have set your equation up like I have with a 1 here, this number is your limit to growth. So whatever number you have in the numerator will be the top asymptote. The bottom asymptote is going to be at 0. The top asymptote will be at whatever number is up there. So if there's a 6 up there, then that means you're capping at 6. Now, I have told you that the limit to growth, one of the pieces of given information is the limit to growth is 5. So doesn't that tell me right now that my equation has a 5 up in the numerator? Can I go ahead and fill that in right now? That's the limit to growth. Now I've got 2 points. Okay, so that I've taken care of that. Now I've got 2 points. And you've done enough of this to know I'm probably going to pick one of those and plug it in, right? Which one do you think I'm probably going to pick first, to plug in first? The one with a 0, because zeros are always easy. So I'm going to plug in the point 5/4 for y and 0 for x. So I have my equation. I filled in my limit to growth. Now I'm doing my initial value point, my y-intercept point. And what's nice about that? Well, the c is gone. So now I have this, right? Which I can solve by simply cross multiplying. So 5 plus 5b equals 20. So 5b equals 15. It looks like b equals 3. You okay with that? All right, so now my equation, I'm down to y equals 5 over 1 plus 3c to the x. I figured out my A value. I didn't have to figure it out. A is the limit to growth every time, okay? And then I did this work and figured out that B was 3. I'm almost done. What do you think I'm going to do now? I'm going to plug in my other point. And what's that going to do? That's going to help me figure out C, hopefully. Let's see. So 20/79 equals 5 over 1 plus 3C to the negative second. Now, you are not going to move that C. You want to? It's negative. You say, ooh, I don't like that negative exponent. That's something else. You got to keep it. You cannot move that negative. You can't move that C because it's hooked to something with a plus sign. So what we're going to do is leave it and cross multiply. So I have 20 plus 60C to the negative second, cross multiplying, and 79 times 5. What is that? 395. Is that right? I don't trust my arithmetic. Yeah. So 60C to the negative second equals what? 375? And C to the negative second is 25/4. I'm just doing arithmetic here. I subtracted 20 and divided by 60. Now what? So maybe 1 over C squared equals 25/4. So 25C squared equals 4 and C squared equals 4/25. Now, some of you are going to go straight from here to here, and that's okay, because you know what that negative does, it turns it over. So if C to the negative second is 25/4, then C to the positive second will be 4/25, which means C is what? 2/5. Isn't that nice how that all worked out? So our final answer is 1 plus 3 times 2/5 to the x plus 1 under 5. What do you think about that? A lot of work. Limit to growth is your numerator. Use your y-intercept next, your initial value, and then plug in that third point. Okay? All right. There's some of those in the homework. Give them a shot. Try them. You should probably by now be pretty well good with 3.1, and you can start 3.2. If there's something in there we haven't covered, you might have a question, ask.